Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through space, time, and one of the most beautiful and misunderstood ideas in modern science, the theory of relativity. For now, imagine leaving the noise of the day behind and arriving at a long, quiet railway line at night. Signals glow in the distance. The rails stretch away until they seem to meet under the stars. Nothing about the scene looks strange at first. If a train rolls past, you know how to describe it. The platform is still, the train is moving, and if someone inside throws a ball forward, you can add the speed of the ball to the speed of the train. This is the ordinary intuition of motion. It is the kind of intuition that works so well in daily life that it feels almost like common sense written into nature. But now, replace the thrown ball with a flash of light. A lamp inside the train sends a pulse forward, and another lamp on the platform sends a pulse along the track. What should happen? If light behaved like the ball, then the pulse from the moving train ought to gain speed from the train's motion. A person on the platform should measure it racing ahead a little faster than light from the stationary lamp. That would be natural. That would be simple. And it is not what the universe allows. The central surprise of special relativity is that light in vacuum has the same speed for every inertial observer, no matter how the source is moving. An inertial observer is simply one who is not accelerating, one who can consider themselves moving at a steady velocity. For all such observers, the speed of light in empty space is not a negotiable measurement. It is exactly 299,792,458 meters per second. The number is so important that modern units define the meter through it. In a quiet way, the speed of light has become part of the ruler by which we measure the world. This sounds impossible at first because everyday speeds do add. A walking person on a moving walkway is faster relative to the floor than someone standing still. A car thrown forward from a truck would carry the truck's motion with it. But light refuses that pattern. Whether the lamp is fixed to the platform or carried on a passing train, an observer who measures carefully in their own inertial frame finds the same vacuum light speed. The universe is not making a small adjustment to our usual rules. It is asking for a different geometry. To understand why, we need to notice what measurements actually require. Speed is distance divided by time. If the speed of light must remain the same for observers moving relative to one another, then distance and time cannot both remain absolute in the old sense. Something has to give. The train observer and the platform observer can no longer share a single universal clock and a single universal ruler while also agreeing on light. Instead, their measurements of space and time must shift together. That shift is the beginning of spacetime. Space and time are not destroyed, and they do not become vague or subjective. A better way to say it is that each observer slices the same physical reality in a different way. One observer's measurement of distance and another observer's measurement of duration can disagree, but the deeper space-time relationship remains consistent. Relativity is often misunderstood as a theory where everything depends on opinion. In truth, it is a theory built around what does not change. Here is the surprising part. The old picture treated time as a single river flowing at the same rate for everyone, everywhere. Special relativity replaces that with a more careful idea. Clocks are physical objects, and their readings depend on the path they take through space-time. A clock sitting with you measures your proper time, the time along your own path. Another clock moving steadily past you is measured differently from your frame. The effect is not a trick of eyesight, and it is not caused by the clock being damaged. It follows from the same rule that keeps light moving at the same vacuum speed. You can begin to feel the shape of the idea with a line of synchronized clocks along the railway. Suppose the platform has clocks placed at regular intervals, all synchronized in the platform frame. To measure the speed of a passing light pulse, the platform observer notes where the pulse is and when it passes each clock. Inside the train, another set of clocks can be synchronized by the passenger's own rules. Both observers build careful systems. Both do real physics. Yet because they are moving relative to each other, their definitions of at the same time across separated places do not match. This is called the relativity of simultaneity, and it may be the most quietly unsettling idea in the opening doorway of relativity. Two distant events can be simultaneous for one inertial observer and not simultaneous for another. That does not mean causality has broken. If one event can actually cause another, all observers still agree on their order. But for events too far apart to influence each other in time, the word now is not universal. It belongs to a frame. Think of two flashes of lightning striking the ends of a long train. A person at the midpoint of the platform may receive the light from both flashes at the same moment and, after accounting for equal distances, conclude that the strikes were simultaneous in the platform frame. A passenger at the midpoint of the moving train is traveling toward one flash and away from the other. The passenger does not build the same slice of time through the two events. The important point is not merely that light takes time to arrive. The deeper point is that once the speed of light is fixed for both observers, their complete systems of clock synchronization disagree. This is where the story changes from a puzzle about light into a story about reality's structure. In older physics, space was a stage and time was a separate clock above the stage. Objects moved, forces acted, and everyone could agree on the same background ticking. In special relativity, the stage and the clock are woven together. Events do not simply happen in space and then receive a time label. They happen in space-time, and different observers moving steadily relative to one another split that space-time into space and time in different ways. A map can offer a gentle comparison. If you draw the curved Earth on a flat page, different map projections preserve different features. One may keep angles reliable while stretching areas near the poles. Another may keep area relationships while distorting shapes. The Earth itself has not changed. The representation has. In relativity, the analogy has limits because space-time is not just a drawing choice. The measurements are physical. But the comparison helps with one essential idea. Two descriptions can differ while still referring to the same underlying structure. The mathematical tool that connects these descriptions is called the Lorentz transformation. It replaces the older Galilean transformation when relative speeds become a significant fraction of light speed. The Galilean version assumes time is shared by everyone, so only positions need to be adjusted between moving frames. The Lorentz version mixes space and time. It says that if you change from the platform frame to the train frame, the time coordinate and the space coordinate are linked. Neither stands entirely alone. At normal human speeds, this mixing is so small that daily life hides it from us. A car on a road, a person walking through a room, even a passenger jet crossing an ocean, all move far too slowly compared with light for length contraction or time dilation to become obvious to the unaided senses. This is why the older rules feel true. They are excellent approximations in the slow world we evolved to notice. Relativity does not erase ordinary experience. It explains why ordinary experience is a special, low-speed corner of a larger patterns. Consider what that really means. The reason a kitchen clock, a wristwatch, and a train station clock seem to share one common time is not because universal time has been proven by daily life. It is because daily motion is tiny beside 299,792,458 meters per second. The small comparison between ordinary speed and light speed is almost nothing for most motion around us. The deeper geometry is present in every moment, but it is usually too subtle to feel. Still, it can be measured. Atomic clocks, particle experiments, and satellite navigation all reveal that these effects are real. A clock in orbit around Earth does not keep exactly the same time as a clock on the ground. Part of the difference comes from its speed, which is special relativity, and part comes from its altitude and Earth's gravitational field, which belongs to general relativity. GPS works only because engineers account for both. The quiet directions on a phone depend on a universe where time is not quite the same for every path. This corrects a common misunderstanding. Relativity is not an exotic theory reserved for black holes, galaxies, or spaceships traveling near light speed. Its effects are usually small, but the principles are woven into modern measurement. The same idea that begins with a light pulse on a train platform ends up inside the timing system that lets satellites tell us where we are. There is something beautiful in that. The most abstract shift in our understanding of time becomes a practical correction measured in microseconds. Before moving deeper, it helps to hold on to one central thread. Special relativity begins with a refusal. Light refuses to be treated like a thrown object. To preserve that fact, nature gives up the old idea of universal simultaneity and replaces it with a space-time structure where moving observers measure space and time differently. But the theory does not make reality loose. It makes reality more precise. Beneath the disagreements about clocks and rulers, there are invariants, relationships all inertial observers can agree on. One of those invariants is the space-time interval. You do not need the full equation yet to understand the role it plays. It is a way of combining separation in space and separation in time so that all inertial observers agree on the result, even when they disagree about the individual pieces. One observer may say two events are separated by a certain distance and a certain duration. Another, moving relative to the first, may assign different values. But the combined space-time relationship remains fixed. The disagreement has rules. That is the calm center of the theory. Relativity does not say that measurements are meaningless. It says measurement is relational, and the relations obey a strict geometry. In the same way that north and east can change depending on how you rotate a map, while the distance between two towns remains a fact of the surface. space and time can mix between observers while space-time keeps its deeper order. The universe is less like a clock hung above a stage and more like a four-dimensional landscape through which every clock traces a path. Now, let the railway fade and imagine two clocks instead. One remains beside you on Earth. The other is placed inside a spacecraft moving steadily past. If you could compare them from your frame, the moving clock would tick more slowly than the one at rest with you. This is time dilation, and it is not a matter of poor visibility or delayed signals. It is a difference in measured elapsed time that follows from the geometry of space-time. Every clock is included in this rule. A clock with gears, a quartz watch, an atomic clock, a beating heart, a chemical reaction, and the decay of an unstable particle are all physical processes. If a system is moving relative to your inertial frame, the processes inside it are measured from your frame as taking longer. The moving observer does not feel slowed. Locally, their own clock ticks normally, their own thoughts move normally, and their own instruments behave normally. Time dilation is not something a traveler notices by looking down at their watch. It appears when different paths through space-time are compared. The phrase proper time is useful here. Proper time is what a clock measures along its own path. If a traveler carries a diary and writes one page each day according to the clock on board, that diary records the traveler's proper time. Someone who stayed on Earth may record more pages between the same departure and reunion events. Neither diary is fake. They follow different paths, and space-time assigns different elapsed times to those paths. This sounds strange because ordinary life has trained us to treat time as a shared account. If two people leave a room and return, we expect them to have aged by the same amount, except for biological details. Special relativity says the path matters. Motion changes how much time a clock accumulates between events. The difference is tiny at ordinary speeds, but it grows as speed approaches the speed of light. A simple number helps. At 0.8 times the speed of light, the Lorentz factor is about 1.67. That means a moving clock, as measured from the frame where the trip distance is at rest, accumulates less time by that factor. If a traveler went to a star 8 light-years away at 0.8 times light speed and came back at the same speed, Earth would measure 20 years for the round trip. The traveler would experience about 12 years. The reunion would not be a matter of perspective. The traveler would be younger. This is the famous twin paradox, though the name is a little misleading. There is no true contradiction. The stay-at-home twin can be treated, in the simplified story, as remaining in one approximate inertial frame. The traveler must change frames to turn around and come back. That change breaks the symmetry. The deeper explanation is geometric. The twins take different paths through space-time, and those paths contain different amounts of proper time. The surprising part is that the straight path in space-time has the most proper time, not the least. In ordinary space, a straight line is the shortest route between 2 points. In flat space-time, the inertial route between two shared events gives the greatest elapsed proper time. The traveler who accelerates away, turns around, and returns follows a bent world line. That path accumulates less time. Relativity asks us to learn a new kind of distance, one that includes time as part of the geometry. This also corrects another common misunderstanding. Acceleration is important in the twin story, but not because it damages the clock or mechanically slows the traveler. A perfect clock would show the same result. Acceleration marks the change in inertial frame. During the turn, the traveler's way of assigning distant Earth time changes. Their slice of now across space rotates, so to speak, because simultaneity depends on motion. The clock difference comes from the full space-time path, not from a clock being stressed. A train switching image can help if used gently. A traveler going east on one train, then switching to a train going west, has changed their frame of motion. In everyday travel, that change only alters ordinary coordinates and schedules. At relativistic speeds, changing frame also changes which distant events count as simultaneous. The limitation of the comparison is important. Train timetables are conventions, but relativistic simultaneity is built into physical clock synchronization. Still, the image helps show why the traveler is not symmetric with someone who never changes trains. Time dilation is not only a thought experiment. Fast-moving muons, unstable particles created high in Earth's atmosphere, reach the ground in greater numbers than they would if ordinary time rules held. In their own short proper lifetimes, they should not survive the journey easily. From Earth's frame, their internal decay clocks are slowed by their high speed. From the muon's point of view, the atmosphere is length contracted. Both descriptions are different slices of the same space-time fact, and the detectors on the ground receive the evidence. Atomic clocks bring the same principle into human scale. Modern precision clocks can detect tiny differences caused by motion and by gravitational potential. NIST has measured relativity at scales so small they feel almost personal. Clocks separated by modest height differences and motion of only meters per second can reveal measurable changes. The effect across a human lifetime may be only fractions of a second, but the point is profound. Time is not an abstract background. It is a measurable physical quantity sensitive to path and place. Now imagine a ruler moving past you along the railway. If it is at rest in its own frame, it has its proper length. But if you measure it from the platform while it is moving, you must record the positions of both ends at the same time in your frame. Because simultaneity differs between frames, that measurement gives a shorter length along the direction of motion. This is length contraction. Length contraction is often pictured poorly, as though the object is being squeezed by a force. That is not the right image. In its own rest frame, the ruler is unchanged. Its atoms are arranged normally. Its proper length is what someone riding with it measures. The contraction appears when another frame measures the moving object using that frame's rule for simultaneous endpoint positions. The object is not crushed. The measurement geometry has changed. Only the direction of motion contracts in the standard treatment. A spacecraft moving past you is measured shorter along its direction of travel, not squeezed equally in all directions. At low speeds, the change is far too small to notice. Near light speed, the effect becomes dramatic. But even then, seeing and measuring are not the same. A photograph of a fast object can be distorted by light travel time and perspective. Length contraction is a precise frame measurement, not merely a visual squashing. The theme is becoming clear. Time dilation, length contraction, and relativity of simultaneity are not separate magic tricks. They are three faces of one structure. If light speed is invariant, then clocks, rulers, and simultaneity must transform together. Nature does not adjust one piece at a time. It changes the geometry that tells all pieces how to relate. At this point, it is tempting to ask what remains solid. If clocks and rulers depend on motion, what can we trust? Relativity's answer is careful and elegant. Trust the invariant relationships. The speed of light in vacuum is invariant. The space-time interval is invariant. Proper time along a path is physically real. The laws of physics take the same form in inertial frames. The old absolutes were not all wrong because certainty is impossible. They were wrong because the deeper certainty was hidden underneath. Now the journey turns toward energy. Imagine holding a small object in your hand, ordinary and still. It may be a stone, a coin, or a sealed battery. In older thinking, its mass is one property and its energy is another. Energy is what something has when it moves, heats, shines, or reacts. Mass is what gives it weight and resistance to acceleration. Relativity reveals that this separation is not fundamental. Einstein's most famous equation, E equals mc squared, tells us the rest energy of an object. If an object has invariant rest mass m, then even when it is not moving, it contains rest energy equal to its mass multiplied by the speed of light squared. Because c squared is enormous, a small amount of mass corresponds to a vast amount of energy. 1 kilogram of rest mass corresponds to about 9 times 10 to the 16th joules. This does not mean matter is simply a vague substance called energy. That phrase is too loose. Matter has properties such as charge, spin, and quantum numbers. A better statement is that mass is a form of energy, specifically rest energy, and that energy and mass are related within a deeper relativistic framework. The fuller relation includes momentum. Total energy squared equals momentum times c squared plus rest mass energy squared. For an object at rest, the momentum part is zero, leaving the famous simple equation. In nuclear physics, this becomes visible. When protons and neutrons bind together inside a nucleus, the mass of the bound nucleus is slightly less than the mass of the separated parts. The difference is called the mass defect, and it corresponds to binding energy. That energy has been released or would need to be supplied to separate the nucleus again. The missing mass has not vanished mysteriously. It has appeared as energy in the surrounding physical processes. This is why nuclear reactions can release so much more energy than chemical reactions. Chemistry rearranges electrons and bonds outside nuclei. Nuclear fission and fusion rearrange the binding of the nucleus itself, where energy scales are far larger. Uranium-235 fission releases roughly 200 million electron volts per event, a tiny amount by everyday units, but enormous for a single atomic nucleus. Fusion in stars releases energy because the final bound system has less mass energy than the initial ingredients. Annihilation offers another window. When an electron and a positron meet under the right conditions, their rest energy can become photons, usually gamma rays, while energy and momentum are conserved. This is sometimes described as mass becoming pure energy. But even here, the careful language matters. The original particle's rest energy changes form. The resulting photons carry energy and momentum. The laws do not become mystical, they become more unified. If special relativity reshapes motion, time, and energy, general relativity reshapes gravity. To enter that part of the story, imagine stepping into a sealed elevator far from any planet. If rockets pull the elevator upward with an acceleration equal to Earth's gravity, your feet press against the floor. A dropped object falls to the floor. A scale under your shoes reads a familiar weight. Without looking outside, the feeling is remarkably similar to standing on Earth. This is the seed of the equivalence principle. Locally, the effects of gravity and acceleration can be indistinguishable. Einstein realized that this was not a small coincidence. It suggested that gravity might not be a force in the same sense as other forces. In general relativity, gravity is described as the curvature of space-time caused by matter and energy. Objects moving freely follow geodesics, the straightest possible paths through that curved geometry. In everyday language, gravity feels like a pull. A dropped stone accelerates downward. The moon orbits Earth. Earth orbits the sun. But in general relativity, Earth is not being tugged by an invisible rope. It is following a path through space-time shaped by the sun's mass energy. The sun shapes the geometry, and Earth moves along that geometry. The result looks like an orbit. The phrase straightest possible path may sound odd in curved space-time. A map can help again. On Earth's surface, the shortest route between two distant cities may appear curved on a flat map because the map projection distorts the surface. Airplanes often follow great circle routes, which are straight in the geometry of the sphere but curved on many maps. In general relativity, free-falling objects follow geodesics in space-time. The comparison is limited because space-time includes time as well as space, but it helps soften the idea that a curved path can be the natural straightest path in the right geometry. This description changes our understanding of falling. An astronaut in orbit feels weightless, not because gravity is absent, but because the astronaut and spacecraft are falling together along a geodesic. Earth is continuously curving their path. They keep missing the ground because they have enough sideways motion. In their local frame, floating inside the spacecraft, there is no floor pushing upward. That is why orbit feels weightless, even though Earth's gravity is still very much present. The equivalence principle is local. Over small regions, a freely falling laboratory can behave as if gravity has disappeared. Over larger regions, tidal effects reveal the difference. Earth's gravity pulls slightly toward Earth's center from different directions at different locations. A person in a long falling elevator could, in principle, measure tiny differences between the pull at the top and the bottom. Those differences are not removed by choosing a falling frame. They are signs of space-time curvature. General relativity predicts that time itself is affected by gravity. A clock deeper in a gravitational field ticks more slowly relative to a clock higher up. This is gravitational time dilation. On Earth, the effect is small, but precise clocks can measure it. A clock on a mountain runs slightly faster than one at sea level because it is higher in Earth's gravitational potential. The difference is tiny, yet it is not optional. It is part of how time works in curved spacetime. GPS again becomes a quiet test of the theory. Satellites orbit high above Earth, where gravity is weaker, so their clocks run faster than comparable clocks on the ground by roughly 45 microseconds per day. Their orbital speed produces special relativistic time dilation in the other direction, slowing them by about 7 microseconds per day. The net effect is about 38 microseconds per day. That sounds small, but light travels many kilometers in that time. Without correction, navigation would quickly drift. So, a phone locating you on a road is doing more than receiving radio signals. It is relying on a corrected clock network in curved space-time. The theory that began with thought experiments about light and elevators has become part of ordinary engineering. This is one of relativity's quiet gifts. It turns wonder into measurement. General relativity also predicts that light bends near mass. This does not happen because photons have rest mass in the ordinary sense. It happens because light follows paths through curved space-time. If a beam passes near the sun, its route is deflected. For light grazing the sun's limb, the predicted deflection is about 1.75 arc-seconds. A tiny angle, but a historically enormous clue. In 1919, eclipse expeditions led by Arthur Eddington and others measured starlight near the sun during a total solar eclipse. The early results had uncertainties, and later history has treated them with care, but the event became a public turning point. The image was simple enough to carry into newspapers. The sun bends starlight, and Einstein's theory predicts how. Since then, light bending has been confirmed far more precisely by modern methods. Mercury offered another test. Its orbit slowly precesses, meaning the closest point of its path around the sun shifts over time. Most of that shift can be explained by Newtonian gravity and the pulls of other planets. But an extra 43 arc-seconds per century remained. General relativity accounted for it through the curvature of space-time near the sun. A tiny mismatch in a planet's orbit became evidence that gravity was not exactly what Newton had imagined. Gravitational redshift gave another route. Light climbing out of a gravitational field loses energy and shifts toward longer wavelengths. Clocks lower in gravity tick slower relative to clocks higher up, and the frequency of light reflects that difference. The Pound-Rebka experiment measured gravitational redshift over a height of 22.5 meters on Earth. Later experiments, including Gravity Probe A and modern optical clocks, pushed such tests further. Frame dragging adds a subtler effect. A rotating mass can drag local inertial frames slightly around with it. The image of stirred honey can help, but only as a first picture. Space-time is not a sticky fluid. Around Earth, the effect is tiny. Gravity Probe B used extremely precise gyroscopes in orbit to measure both the geodetic effect from motion through curved space-time and frame dragging from Earth's rotation. The results were consistent with general relativity, though frame dragging was measured less precisely than originally hoped. Then came gravitational waves. General relativity predicts that accelerating masses, especially compact objects in violent motion, can send ripples through space-time. For decades, the evidence was indirect. The Hulse-Taylor binary pulsar showed orbital decay consistent with energy lost to gravitational waves. Then on September 14, 2015, LIGO directly detected waves from merging black holes. The signal was not light. It was a stretching and squeezing of space-time itself passing through Earth. The scale of that detection is almost difficult to hold. LIGO's long arms watched for changes far smaller than the width of a proton, caused by a merger more than 1 billion light-years away. The wave had crossed space for longer than complex life has existed on Earth, then moved through the detectors as a whisper in geometry. Here the poetry belongs to the science, because the measurement itself is quiet and extraordinary. Black holes enter the story not as monsters, but as solutions of general relativity. A black hole is a region where space-time is curved so deeply that beyond a boundary called the event horizon, no signal can escape to distant observers. The horizon is not a surface made of matter. It is a causal boundary. Outside it, some paths can still lead outward. Inside it, all future-directed paths lead deeper in. From far away, a black hole's gravity behaves like the gravity of any other object with the same mass. This corrects a common myth. Black holes are not cosmic vacuum cleaners. If the Sun were somehow replaced by a black hole of the same mass, Earth would not suddenly spiral inward. It would keep nearly the same orbit, though the loss of sunlight would change everything for life. The danger of a black hole is not magical suction. It is closeness, curvature, and the loss of outward paths near the horizon. The event. Horizon Telescope gave humanity another kind of test: images of black hole shadows. In 2019, the collaboration released the image of M87 star, the supermassive object in the galaxy M87. In 2022, it released an image of Sagittarius A star, the compact object at the center of the Milky Way. These images do not show a solid surface. They show glowing material and light paths shaped around a dark central region, consistent with predictions from general relativity. Gravitational lensing carries the same idea across the cosmos. Massive galaxies and clusters curve space-time enough to bend light from objects behind them. Sometimes this creates arcs, multiple images, or even Einstein rings when alignment is especially close. Weak lensing subtly distorts the shapes of many background galaxies, letting astronomers map mass, including dark matter, that does not shine. The universe becomes its own telescope, with gravity shaping the view. Now widen the journey until galaxies themselves become points in a larger pattern. General relativity is not only a theory of planets, clocks, and black holes. It is also the framework for modern cosmology. The expanding universe is described not as galaxies flying through pre-existing space from a central explosion, but as the growth of the scale factor, the changing distance between co-moving points in space. The rising bread dough analogy can help. Raisins embedded in dough move farther apart as the dough expands, and each raisin can see the others receding. The limitation matters. Bread expands into an oven, while the universe is not necessarily expanding into an outside room. But the comparison gives one useful idea. Cosmic expansion is not simply ordinary motion through space. It is the changing geometry of space on large scales. This distinction explains one of the strangest sounding facts in cosmology. distant galaxies can recede from us faster than light because of the expansion of space. This does not violate special relativity because no local object is moving through its nearby space faster than light. The rule against faster-than-light travel applies locally to motion and signals. Metric expansion is a different concept. Space itself can carry distant galaxies apart in a way that makes their recession speed exceed light speed. The age of the observable universe is about 13.8 billion years, but the observable universe is larger than 13.8 billion light-years in radius because space has expanded while light has traveled. That fact often feels counterintuitive. A photon may spend billions of years crossing space while the space between source and observer stretches during the journey. Cosmology requires us to think not only about motion in space, but about the changing space-time background itself. Dark matter and dark energy belong carefully in this story. General relativity describes how mass energy affects geometry and how geometry affects motion. Observations indicate that ordinary matter is only a small fraction of the cosmic energy budget. Dark matter helps explain gravitational behavior in galaxies and clusters. Dark energy is associated with the accelerated expansion of the universe, but their fundamental nature remains unknown. GR gives the framework. It does not by itself identify what these components are. The Hubble tension is one of the active research questions at the boundary of modern cosmology. Different methods for measuring the current expansion rate of the universe give values that do not perfectly agree. Early universe measurements and local distance ladder measurements point towards slightly different numbers. This may reveal unknown systematic error, or it may be a hint of new physics. The responsible tone is curiosity without overclaiming. The measurement tension is real. The explanation is not settled. At the edge of relativity, singularities appear. In classical general relativity, black hole centers and the beginning of the Big Bang can lead to places where curvature and density become infinite. Most physicists treat such infinities as signs that the theory is being pushed beyond its domain. General relativity is classical. It does not include quantum mechanics in a complete way. At extreme scales, especially near the Planck scale, a deeper theory is expected. Quantum gravity is the name for that missing bridge. It would unify the geometric gravity of general relativity with the quantum rules that govern microscopic physics. Candidate approaches include string theory, loop quantum gravity, and other research programs, but none has been confirmed as the final answer. This is active research, not settled science. The honest wonder lies in the open question itself. Two of the most successful frameworks in physics do not yet fit together completely. Before we step into science fiction, it is worth lingering with the measurements because relativity is sometimes treated as if it were mostly a set of strange thoughts. In reality, the theories survived because clocks, particles, planets, and light kept answering in the same direction. A good scientific idea must do more than sound deep. It must meet the world precisely enough that the world has a chance to disagree. Imagine carrying two atomic clocks onto airplanes and sending them around Earth in opposite directions. That is the spirit of the Hafeel-Keating experiment from 1971. One set of clocks flew eastward, one westward, and after the flights they were compared with clocks that had remained on the ground. The result had to account for both motion and gravity because the airplanes were moving relative to Earth's surface and also flying at altitude. The shifts were measured in nanoseconds, far too small for a passenger to feel, yet large enough for precision clocks to detect. The eastward and westward directions matter because Earth itself rotates. Flying east means moving faster relative to Earth's center, which increases the special relativistic slowing from speed. Flying west partly subtracts from Earth's rotation, changing the balance. At the same time, flying above the surface places the clocks in a slightly weaker gravitational field, which makes them tick faster relative to clocks lower down. The final result is a delicate sum of two relativistic effects. That is exactly the kind of accounting modern timing systems must do. The experiment is not perfect in the way a clean thought experiment is perfect. Airplanes are messy. Routes, altitude, temperature, and clock handling must be considered. But the value of the story is that relativity left the blackboard and entered a commercial aircraft. It showed that the theory was not only about imaginary travelers near light speed. Even ordinary machines moving through Earth's rotating gravitational field accumulate time in subtly different ways. Now imagine a particle accelerator, where the clocks are not devices with hands or oscillating atoms, but particles with lifetimes. Muons are unstable. At rest, a muon exists for only about 2.2 microseconds on average before decaying. If classical time were all that mattered, fast muons would not behave as they do in laboratories and in the atmosphere. But when muons move close to the speed of light, their lifetimes in the lab frame are extended by the Lorentz factor. The CERN muon storage ring experiments used muons moving at high relativistic speeds and confirmed the expected lifetime extension with striking precision. The muons were not protected by a shell. They were not made more durable in their own rest frame. Their decay process, viewed from the lab frame, was time-dilated. The particle itself became a clock, and the clock followed relativity. This is a useful moment to connect time dilation and length contraction again. From Earth's frame, atmospheric muons live longer because their internal clocks run slow. From a muon's own frame, the trip through the atmosphere can be described differently. The atmosphere's thickness is contracted along the direction of motion. The muon does not need an unusually long lifetime in its own frame because the distance to the ground is shorter in that description. Both stories are valid within their frames. They are two ways of reading the same space-time geometry. That is one of the quiet strengths of relativity. It lets different observers tell different coordinate stories without contradicting the final event. The muon reaches the detector, or it does not. The twins reunite with different ages, or they do not. The satellite clock gains time relative to the ground, or it does not. Relativity is not a permission slip for any story. It is a rule book for which different stories can describe the same physical result. A similar discipline appears in particle accelerators. As particles approach the speed of light, adding energy does not make them simply gain speed in the old linear way. Their speed creeps closer to light speed, while their energy and momentum continue increasing. This is why modern physics avoids the phrase relativistic mass when possible. The invariant rest mass remains the same. The particle's total energy and momentum change. That language is cleaner, and it prevents a common misconception that mass itself simply swells like a balloon. If you could watch a beam inside an accelerator, you might imagine it as a river of particles guided by magnetic fields. But the magnets cannot be designed with ordinary low-speed formulas. The particles' momentum is relativistic. Their energy, their path curvature, and their timing all depend on the same framework that began with light on a train. A machine built to test the smallest known structures must respect the geometry of space-time to function at all. Mass-energy equivalence also becomes practical in nuclear measurements. Consider a helium-4 nucleus made of 2 protons and 2 neutrons. The bound nucleus has less mass than the 4 separated particles would have by themselves. The difference corresponds to about 28.3 million electron volts of binding energy. That energy is not decorative. It is the energy that would be needed to pull the nucleus apart, and it is the energy released when the bound state forms under the right conditions. Iron sits near the peak of binding energy per nucleon, which is why it plays such a central role in stellar evolution. Fusion of light elements can release energy as nuclei move toward more tightly bound arrangements. Fission of very heavy elements can also release energy by moving toward more tightly bound fragments. The same mass-energy accounting connects the sun's steady light, nuclear reactors, supernova cores, and particle collisions. Relativity did not invent nuclear energy, but it gave the language that makes the bookkeeping exact. This is also why the phrase, small mass difference, can hide a huge reality. In everyday units, the mass lost in a nuclear reaction may be tiny, but multiplying by c squared converts that tiny mass difference into a large energy release. The symbol c is already immense. Squaring it makes the conversion factor enormous. A quiet equation turns into the heat of stars. Now return to gravity, but this time imagine the orbit of Mercury as a slow drawing traced around the Sun. If you could watch the planet's path over centuries, the ellipse would not close perfectly. Its closest point to the Sun would rotate, making a rosette-like pattern. Newtonian gravity explains most of that precession through the influence of other planets. But it leaves a small extra amount, about 43 arcseconds per century. An arcsecond is tiny. 1 degree is divided into 60 arc minutes, and each arc minute into 60 arc seconds. 43 arc seconds spread over a century is an almost whispering discrepancy. Yet that whisper mattered because Mercury moves close to the Sun, where space-time curvature is stronger than it is for more distant planets. General relativity accounted for the extra precession. The correction was small, but it landed exactly where the old theory had been incomplete. The lesson is important for the whole channel of thought. The scientific revolution does not always begin with a giant, visible failure. Sometimes it begins with a tiny mismatch that refuses to go away. Mercury's orbit did not behave wildly. It behaved almost Newtonian. But the almost was enough. General relativity did not merely offer a new metaphor for gravity. It explained a measured anomaly. The 1919 eclipse gave the public a more visual story. During a total solar eclipse, the moon blocks the sun's bright disk, making it possible to photograph stars appearing near the sun's edge. If the sun bends starlight, then the apparent positions of those stars should shift. General relativity predicted twice the deflection expected from a simpler Newtonian-like treatment of light as particles affected by gravity. The measured results were imperfect, but the direction was clear enough to transform Einstein into a public figure. Modern measurements of light bending are far more precise. Radio signals from distant quasars, spacecraft tracking, and other methods let scientists test how mass bends electromagnetic signals. The basic idea is now routine in astronomy. Gravitational lensing is not a rare curiosity reserved for one eclipse. It is one of the tools by which we study galaxies, clusters, dark matter, and the distant universe. Imagine a cluster of galaxies between Earth and a much farther galaxy. The cluster's mass, including dark matter, curves spacetime. Light from the distant galaxy travels along multiple paths around that curvature. To us, the background galaxy may appear stretched into arcs, split into multiple images, or arranged in a ring if the alignment is especially precise. The foreground mass has acted like a lens, but not by glass refraction. It has changed the geometry through which light travels. Weak lensing is quieter. It does not usually create dramatic arcs that leap from an image. Instead, it slightly shears the shapes of many distant galaxies. One galaxy shape is too irregular to tell much. But statistically, across thousands or millions of background sources, a pattern emerges. The distortions reveal the mass distribution in the foreground. This is how gravity can let us map matter that does not emit light. That idea is one of the great reversals in astronomy. We do not only see what shines, we see what changes the light of something else. A black hole may reveal itself through orbiting stars. A galaxy cluster may reveal dark matter through lensing. A gravitational wave reveals a merger through changing distances between mirrors on Earth. Relativity teaches us to read influence, not just brightness. Now picture gravity probe B in orbit around Earth carrying gyroscopes so carefully made that they were among the smoothest spheres ever produced. A gyroscope tends to keep its axis fixed, but in curved space-time near a rotating Earth, general relativity predicts tiny shifts. One shift comes from Earth's mass-curving space-time, the geodetic effect. Another comes from Earth's rotation, dragging local inertial frames slightly, the frame-dragging effect. The numbers are small, thousands of milliarseconds per year for the geodetic effect, and only about 39 milliarseconds per year for frame dragging. A milliarsecond is 1,000th of an arcsecond. These are not motions you could notice by looking up, yet they are measurable with a sufficiently careful spacecraft. The mission faced technical challenges, but its final results were consistent with general relativity. Again, the theory survived not by being vague, but by making difficult predictions precise enough to test. The Pound-Rebka experiment is quieter but just as revealing. In a tower at Harvard, gamma rays traveled vertically over a height of 22.5 meters. General relativity predicted that the frequency would shift because of the difference in gravitational potential between the bottom and top. The shift was incredibly small, but the experiment used the Mossbauer effect to measure it. A building became a laboratory for curved spacetime. Modern optical clocks have made such ideas even more intimate. They can compare time at height differences that feel almost ordinary. The higher clock runs slightly faster because it is less deep in Earth's gravitational field. The lower clock runs slightly slower. This is not because gravity is pulling on the mechanism like a hand on a gear. It is because time itself, as measured by physical clocks, depends on gravitational potential. If the idea still feels strange, imagine time as part of the terrain rather than a universal metronome above it. Near a massive body, the terrain changes. Clocks trace paths through that terrain, and their readings reflect where they are and how they move. This image is not literal, but it helps with the essential shift. A clock is not outside the universe measuring it from a safe balcony. It is inside the universe, subject to geometry. Black holes sharpen the same lesson. Outside a black hole, a distant observer sees light from infalling matter become increasingly redshifted and delayed as it approaches the horizon. The object appears to fade and slow. But an infalling observer crosses the horizon without seeing their own clock stop. Their proper time continues. The two descriptions sound incompatible only if we assume there must be one universal external time that everyone shares. Relativity tells us to compare frames and paths carefully. At the horizon, the coordinate description used by a distant observer can become awkward. Some coordinates make the horizon look like a place where time freezes. Other coordinate systems pass smoothly through it. The physical truth is subtler than a simple phrase like, "time stops." For the falling observer, nothing magical happens at a large black hole's horizon at the exact crossing moment, though tidal forces may become important depending on the black hole's mass. For the distant observer, signals from near the horizon become redshifted and delayed without end. The singularity deeper inside is different. Classical general relativity predicts that curvature becomes infinite there, at least in the simplest black hole solutions. That is not a comfortable physical result. Infinite density and curvature usually signal that a theory is being pushed beyond where it can speak. Most physicists expect quantum gravity to change the story near such extremes, but no confirmed theory yet tells the final answer. Rotating black holes add another layer. Real astrophysical black holes are expected to spin. A rotating black hole is described by the Kerr solution rather than the simplest Schwarzschild case. Rotation creates an ergosphere outside the event horizon, a region where spacetime is dragged so strongly that objects cannot remain still relative to distant observers. This does not mean they must fall in immediately, but it does mean the geometry itself is being swept around by spin. Accretion disks around black holes are among the brightest engines in the universe. Matter falling inward usually has angular momentum, so it forms a hot rotating disk rather than plunging straight down. Friction, turbulence, and magnetic fields heat the gas to extreme temperatures. Much of the light we associate with black holes comes from material outside the horizon before it crosses the boundary. The hole itself is dark. The environment can blaze. Jets from some black hole systems reveal the role of magnetic fields in rotation. Narrow streams of particles can be launched from regions near the accretion disk and black hole, sometimes extending far beyond the host galaxy. The exact physics is complex, but the broad picture connects gravity, plasma, magnetism, and relativity. A black hole is defined by what cannot escape from inside the horizon, yet some of the most powerful visible structures in the cosmos arise from what happens just outside it. Gravitational waves from black hole mergers gave scientists a new way to listen to these systems. Before LIGO, black holes could be inferred through light from surrounding matter or through the motion of companion stars. After direct gravitational wave detection, pairs of black holes that emitted no ordinary light could still reveal themselves by shaking spacetime. The final moments of a merger are governed by strong field general relativity, where the equations become nonlinear and numerical simulations are essential. When two black holes spiral together, they lose orbital energy through gravitational waves. Their orbit shrinks, the frequency rises, and the signal becomes a chirp. At the end, the horizons merge and settle into a single distorted black hole that rings down like a struck bell returning to quiet. The ring-down frequencies depend on the final object's mass and spin. This gives physicists a way to test whether the remnant behaves like a general relativistic black hole. Neutron-star mergers add matter to the gravitational wave story. Unlike black holes, neutron stars have surfaces and dense nuclear material. When they merge, they can produce gravitational waves, gamma rays, kilonova light, and heavy elements. This multi-messenger astronomy connects space-time ripples with telescopes across the electromagnetic spectrum. Relativity becomes part of a larger cosmic event, where gravity, nuclear physics, and light all speak at once. Now move outward again to the structure of the universe. The expanding cosmos is not expanding from a center into empty surroundings. Every calm-moving observer on large scales sees distant galaxies receding. The farther away a galaxy is, the faster its recession appears, according to the Hubble-Lemaitre law. This does not place us at the center. It is what expansion looks like from any typical point in a uniform expanding space. The cosmic microwave background gives a snapshot of the early universe when it became transparent, about 380,000 years after the Big Bang. Before that time, photons scattered constantly in a hot plasma. After electrons and nuclei combined into neutral atoms, light could travel freely. That ancient light has been stretched by cosmic expansion into microwaves. It arrives from every direction, carrying tiny temperature variations that seeded the later growth of structure. Those tiny variations are important. The universe is not perfectly smooth. Slightly denser regions pulled in more matter through gravity, growing over billions of years into galaxies and clusters. Dark matter played a central role because it does not interact with light the way ordinary matter does, but it does gravitate. It helped form the scaffolding into which ordinary matter later fell. The galaxies we see are luminous tracers of a deeper gravitational structure. Dark energy enters through the accelerated expansion of the universe. Observations of distant supernovae, along with other cosmological data, showed that expansion is not simply slowing under gravity as once expected. It is accelerating. The simplest explanation within general relativity is a cosmological constant, often associated with vacuum energy. But the true nature of dark energy remains unknown. It is one of the great open questions in physics. This is where humility becomes part of the narration. General relativity has passed every major test so far, but cosmology asks whether we understand all the contents of the universe and the largest scale behavior of space-time. Maybe dark energy is a cosmological constant. Maybe it points to new fields. Maybe some subtle modification of gravity is required. The evidence constrains the possibilities, but the final interpretation remains open. The same careful language belongs to the Hubble tension. Measurements based on the early universe, such as those connected to the cosmic microwave background, suggest one value for the present expansion rate. Local measurements using distance ladders suggest a higher value. The disagreement has persisted enough to attract serious attention. But it is not yet a license for dramatic conclusions. It is a scientific tension, a place where better data and better understanding are still needed. Relativity also clarifies the difference between looking far away and looking back in time. Because light takes time to travel, distant galaxies are seen as they were long ago. The farther we look, the earlier the cosmic era we observe. A telescope is not simply a magnifying glass for space. It is also a time machine in the ordinary light travel sense. This is not time travel into our own past. It is observation delayed by distance. When we observe the cosmic microwave background, we are not seeing the Big Bang itself, but the afterglow from a time when the universe became transparent. Earlier moments are hidden from ordinary light because the plasma was opaque. To probe earlier epochs, scientists use indirect evidence, element abundances, gravitational waves in principle, inflationary signatures, and particle physics. The beginning of the universe is not a single picture. It is a layered inference. Inflation, the idea that the early universe underwent a rapid accelerated expansion, is widely studied because it can explain why the universe appears so smooth and nearly flat on large scales while still containing the tiny fluctuations that became galaxies. But the details of inflation remain active research. Which field drove it, how it began, and how it ended are not settled. Again, the boundary between established observation and theoretical explanation must remain clear. This separation is part of the Hypnos style of science, wonder without overclaiming. It is more calming, not less, to know where the firm ground is. Light speed in vacuum, time dilation, gravitational redshift, lensing, orbital precession, gravitational waves, black hole shadows, and cosmic expansion are well supported. Quantum gravity, singularity resolution, dark energy's nature, and speculative shortcuts through space-time remain open. Science fiction often enters here, with wormholes, warp drives, and time machines. Relativity does allow some mathematical solutions that resemble shortcuts or closed paths through time, but mathematical permission is not the same as physical reality. Traversable wormholes, if they are possible at all, appear to require exotic conditions such as negative energy densities not known to exist in usable amounts. The original Einstein-Rosen bridge is not a practical tunnel for travelers. Warp drive ideas, such as Alcubierre-style metrics, try to move a bubble of spacetime by contracting space ahead and expanding it behind. This is sometimes described as moving the road rather than locally pushing a ship faster than light. But the known proposals require extreme or exotic stress energy conditions. No warp drive has been demonstrated. The right phrase is not "relativity says we can." The careful phrase is "some equations can be written, but the physical requirements remain speculative." Closed time-like curves are another mathematical possibility in some solutions of general relativity. They are paths through space-time that loop back to an earlier event. That sounds like a time machine, but no such structure has been observed, and many physicists suspect quantum effects or chronology protection may prevent practical formation. The story belongs in the boundary chapter, where we distinguish established physics from speculation. The same care applies to tachyons, hypothetical particles that would always move faster than light. They have not been observed, and they would create deep causality problems. In a Sleep Channel documentary, it is tempting to let such ideas become dreamy. But the science is more interesting when it is honest. Relativity is already strange enough without pretending speculation has become engineering. The reason faster-than-light signals are so troublesome is not merely that they break a speed rule. They threaten the order of cause and effect. In relativity, observers moving relative to one another can disagree about the timing of distant events, but they still agree about causal relationships when one event can influence another. Light cones protect that order. If a signal could travel outside the light cone, then in some frames the effect could appear before the cause. The speed limit is also a causality limit. This makes the light cone one of the most useful mental pictures in all of relativity. Imagine an event as a point, a lamp flashing, a clock ticking, a star exploding. From that event, light spreads outward in all directions. In a spacetime diagram, that expanding sphere becomes a cone. The inside of the future cone contains places that can be reached by light or slower influences. The outside cannot be reached from that event without faster-than-light travel. Every event carries this invisible structure around it. The past cone works the other way. It contains events that could have affected the present one. Light from a star enters your eye because the star's emission event lies inside your past light cone. A galaxy too distant for its light to have reached us yet may be real, but it cannot have influenced us by ordinary signals. Relativity turns the question, what exists now, into a more careful question. What can affect what, and along which paths through space-time? This is why the loss of universal now does not make the universe incoherent. A universal now was never the guardian of causality. Light cones are. Different observers can slice space-time into different surfaces of simultaneity, like cutting a loaf at different angles. But they cannot tilt those slices enough to reorder cause and effect inside the light cone. The deep structure remains stable even when the surface description changes. There is a calm, philosophical beauty in that. Relativity removes one kind of certainty, the idea that everyone shares the same cosmic present, and replaces it with a more durable certainty, the causal structure of space-time. It is not the certainty we expected. It is better suited to the universe we actually measure. Practical physics lives inside that structure. Spacecraft navigation depends on signal travel time. Radio communication with Mars cannot be instant because Mars may be many light minutes away. Astronomers studying distant galaxies are studying delayed light, not current conditions, in a universal present. Particle physicists analyzing collisions must conserve energy and momentum relativistically. Engineers building satellite systems must synchronize clocks that do not naturally agree if left uncorrected. Even the definition of a meter carries the imprint of relativity. Because the speed of light in vacuum is fixed, the meter is defined by the distance light travels in a specific fraction of a second. That means the ruler in a laboratory is connected, at the deepest level of measurement, to the invariant speed that forced space and time into a single framework. The ordinary act of measuring length now rests on the very principle that overturned ordinary length. The second two is defined by atomic timekeeping, by the frequency of radiation associated with the transition in cesium atoms. Modern metrology is a world of clocks, light, and invariance. It is not separate from relativity. It is one of the places where relativity quietly became infrastructure. When standards laboratories compare clocks, define distances, or test gravitational redshift, they are maintaining a civilization's agreement with space-time. There is also a useful emotional correction here. Relativity can feel disorienting because it takes familiar words, time, length, mass, gravity, and makes them more subtle. But subtle does not mean unreal. A proper length is real in the rest frame of an object. Proper time is real along a clock's path. Rest mass is invariant. Local measurements are meaningful. The theory does not dissolve the world into uncertainty. It teaches us which question we are actually asking. If you ask, "How long is the moving train?" relativity responds by asking, "Measured in which frame, with which simultaneous endpoints?" If you ask, "How much time passed?" it asks, "Along which world line?" If you ask, "Did those distant events happen at the same time?" it asks, "Simultaneous in which inertial frame?" These are not evasions. They are the precision required when light speed is the same for everyone. That precision is why relativity is still taught through thought experiments. Trains, clocks, elevators, twins, and flashes of light are not childish simplifications. They are instruments for thinking. They remove clutter so that the essential structure can be seen. Then real experiments bring the structure back to the world. Muons, satellites, eclipses, pulsars, gyroscopes, interferometers, and telescopes the size of Earth. The theory also changes our sense of scale. Human life unfolds where speeds are slow, gravity is modest, and time differences are small. We live in a region where Newton and common sense usually work. But the universe is larger than the human scale. Near light speed, near compact masses, across cosmic distances, and inside precision laboratories, the hidden terms become visible. Relativity is the art of not mistaking our local conditions for the whole of reality. From that view, the theory becomes less like a collection of shocks and more like a widening lens. The railway platform is still there. The clocks still tick. The planets still move. But behind them is a larger geometry, one that includes the familiar world as a gentle approximation. That is why relativity can be both unsettling and reassuring. It changes the foundations, but the new foundation is extraordinarily coherent. Now, return to the beginning, to the railway line beneath the stars. A pulse of light moves along the track. The platform observer measures it. The passenger measures it. Against ordinary expectation, both find the same vacuum speed. Around that fact, the old world changes. Simultaneity becomes frame-dependent. Moving clocks accumulate different time. Moving rulers are measured differently. Mass and energy become linked. Gravity becomes geometry. Space itself can expand. The theory of relativity is often presented as a collection of paradoxes, but its deeper character is order. It tells us which quantities depend on the observer and which relationships remain invariant. It does not dissolve reality. It refines it. It says that beneath our familiar intuitions lies a more precise structure, one that only reveals itself when light, speed, gravity, and time are examined closely enough. If you could travel beside a light pulse, relativity says you cannot actually rest with it. Light is not something a massive observer can catch and sit beside. That impossibility is part of the theory's structure. Every massive traveler moves on a time-like path, accumulating proper time. Light follows null paths, with no proper time in the same sense. The separation between these kinds of paths protects causality and shapes what can influence what. Light cones offer a helpful image. For any event, the future light cone contains events that can be reached by light or slower signals. The past light cone contains events that could have influenced it. Outside the cone lie events too distant in space and too close in time to be causally connected. Different observers can slice space-time into different nows, but they agree on the light cone structure. Causes remain inside the geometry. This is one of the reasons relativity is not philosophical looseness. It is strict about communication, influence, and measurement. No message, object, or usable information can locally outrun light in vacuum. That limit is not merely a speed sign posted in space. It is part of the structure that keeps cause and effect from falling apart. Faster-than-light signals would allow different observers to disagree about causal order in dangerous ways. In the quiet laboratory, the same structure is present. A pair of atomic clocks can compare tiny differences in elapsed time. A particle accelerator must use relativistic energy and momentum to steer beams correctly. A spacecraft navigation system must account for signal travel times and relativistic corrections. Relativity is not only a story of cosmic scale. It is also the hidden grammar of precise instruments. Einstein did not arrive at these ideas by adding drama to physics. He followed tensions already present in electromagnetism, measurement, and motion. Maxwell's equations suggested a fixed speed for electromagnetic waves. Experiments failed to reveal the expected motion through an ether. The old framework strained. Special relativity removed the ether and changed the meaning of space and time instead. The result was simpler in principle, but deeper in consequence. Minkowski later gave the theory its geometric language. Space by itself and time by itself, he suggested, were fading into a combined space-time. That is the form in which modern physics often understands the theory. Events are points in space-time. Objects trace world lanes. Clocks measure proper time along those lines. Observers choose coordinate systems, but the geometry underneath does not belong to one observer alone. General relativity extended this geometry from flat space-time to curved space-time. In special relativity, inertial frames in the absence of gravity are central. In general relativity, gravity itself becomes part of the geometry. Matter and energy tell space-time how to curve. Curved space-time tells matter and energy how to move. The phrase is famous because it captures the exchange. The contents of the universe and the shape of the universe are not separate stories. When the geometry is weak, Newton's gravity works beautifully. Planets, projectiles, tides, and many engineering problems can be handled with Newtonian approximations. Relativity does not make Newton useless. It explains why Newton works so well in familiar conditions and where corrections appear. The mark of a deeper theory is often not that it destroys the earlier one, but that it contains it as a limiting case. That pattern repeats across physics. Classical mechanics appears inside relativity at low speeds. Newtonian gravity appears inside general relativity in weak fields and slow motion. Everyday time appears inside spacetime when speeds are small and gravitational differences are modest. Human intuition is not foolish. It is local. It was shaped in a narrow region of reality where the larger structure is mostly hidden. The beauty of relativity is that it lets us step outside that narrow region without abandoning reason. It gives us equations, experiments, and corrections. It tells us why muons survive, why GPS works, why Mercury's orbit shifts, why starlight bends, why black holes can exist, why gravitational waves travel, and why cosmology must treat space itself as dynamic. A single change in the meaning of measurement reaches from a railway platform to the edge of the observable universe. As the journey grows quiet, imagine a line of clocks stretching from Earth to orbit, from the Sun to Mercury, from a laboratory to a distant galaxy cluster. Each clock follows its path. Each beam of light follows space-time's geometry. Each observer measures from a frame, and each frame reveals part of the same world. The old universal now has dissolved, but it has been replaced by something richer, a universe where time is woven into the road. The final lesson is not that reality is beyond understanding. It is that understanding sometimes requires us to release the simplest picture. Space is not merely emptiness where things happen. Time is not merely a master clock above events. Gravity is not merely a pull across a stage. Together they form a structure, and that structure can stretch, curve, ripple, and guide. Tonight, Hypnos has guided us through the first strange doorway: light's fixed speed, moving clocks, shortened lengths, different paths through time, mass as rest energy, gravity as geometry, and the open questions at the edge of known physics. The road began with a train and a flash of light. It widened into space-time, and in that widening, the universe became less familiar, but more precise. So as the railway signals fade and the imagined track disappears into the night, keep one quiet thought from relativity close. The universe does not always match the first shape our senses give it. Yet, when we measure carefully, a deeper order appears. Light keeps its speed. Clocks keep their paths. Geometry keeps its promises. And through space and time, every event finds its place in the vast, exact fabric of space-time.